Our universe should not exist. That is the staggering conclusion many scientists reach when they examine its fundamental rules. Why does the cosmos appear perfectly fine-tuned for life against impossible odds? You are about to journey through the greatest cosmic mysteries, uncovering why the laws of physics seem custom-made for our existence. We will investigate the unnerving precision of the Big Bang, the ghostly influence of dark energy, and the fragile balance that allows atoms to form. By the end, you will understand the profound arguments behind one of science's ultimate questions. Did we win a cosmic lottery, or is there a deeper reason for this perfection? What does it truly mean to live in a universe that feels so deliberately designed? This perfection extends far beyond the fundamental laws of physics. Our cosmic address, it turns out, is also exquisitely fine-tuned. We live within a series of nested Goldilocks zones, each one a region of cosmic real estate that is not too hot, not too cold, but just right for life. The most familiar of these is our planet's position relative to the Sun. Earth orbits within a narrow band where water can remain a liquid, a life-giving oasis between the scorching desert of Venus and the frozen wasteland of Mars. A few percent closer to the Sun and our oceans would boil away. A few percent farther out and they would turn to permanent ice. Our orbit is not the only thing that is just right. Consider our Sun itself. It is a stable, long-lived star, not one of the volatile giants that flare violently and burn out quickly. Our solar system is also remarkably orderly. The gentle gravitational pull of a planet like Jupiter acts as a cosmic vacuum cleaner, deflecting or absorbing countless asteroids and comets that might otherwise pummel our world into extinction. This stability provides the long, uninterrupted stretches of time necessary for life to evolve from single cells into complex, intelligent beings. Even our place in the Milky Way galaxy is perfectly calibrated. We reside in a quiet suburban spiral arm, far from the chaotic and dangerous galactic core, with its intense radiation and frequent supernova. Yet we are also close enough to the inner reaches of the galaxy to have the heavy elements necessary to form rocky planets like our own. From our planetary orbit to our solar system's architecture and our galactic neighborhood, every single layer of our cosmic environment appears to be a sanctuary. This raises a haunting question. Is our universe not only governed by perfect laws, but also filled with perfect places? This delicate balance of our cosmic neighborhood finds its ultimate origin in the universe's very first moment. The Big Bang was not a chaotic explosion, but a burst of creation governed by a perfect recipe. For our universe to exist at all, its initial conditions had to be set with unimaginable precision. One of the most profound of these settings is the universe's flatness. This does not mean it is shaped like a pancake, but rather that the fabric of space itself is exquisitely balanced between two opposing fates. Imagine space as the surface of a vast, expanding balloon. If the universe had too much matter and energy, its gravity would cause space to curve in on itself like a sphere, leading to a catastrophic big crunch. If it had too little, space would curve outward like a saddle, flying apart into a cold, empty void. Our universe, against all odds, is perfectly flat. This perfect flatness points to an expansion that was calibrated to an accuracy of 1 part in a million billion billion billion. The expansion rate itself was the most critical ingredient. It had to be exquisitely balanced, a feat compared to throwing a dart across the entire universe and hitting a bull's eye less than a trillionth of an inch wide. Had the universe expanded even a tiny fraction faster, matter would have flown apart too violently for galaxies and stars to ever form. Every particle would have been flung into an ever-increasing emptiness forever alone. Had it expanded a tiny fraction slower, gravity would have won instantly, pulling everything back into a super-dense inferno within the first second of time. The universe would have collapsed back on itself before it even began. This is not the only impossible perfection in that first moment. The universe was also born in a state of incredibly low entropy, a term for orderliness. This is deeply strange. How do you get a perfectly ordered, low-entropy starting point from what is supposed to be a random, chaotic event? It is like shaking a box of random Scrabble letters and having them spill out to form a perfect Shakespearean sonnet. This initial order is the reason time has a direction and why stars can burn and life can evolve. Without that pristine beginning, the cosmos would have been a formless, high-entropy soup from the start, with no possibility of structure or complexity. So we are left with a staggering realization. The universe we inhabit is not just a product of random chance. It is the result of a launch so precise, so perfectly tuned, that it defies all reasonable probability. Why did our universe begin with this perfect recipe? Was it simply a one in a Googleplex cosmic lottery ticket that we happened to win? Or does this impossible fine-tuning point to a deeper truth about the nature of reality itself? This perfect expansion from the Big Bang, however, was only the beginning of the story. For billions of years, scientists believed the mutual gravity of all the galaxies was gradually slowing the cosmic expansion, like a ball tossed upward slowing as it climbs. Then, in the late 1990s, two separate teams of astronomers made a discovery that shattered this assumption. They found that the universe's expansion is not slowing down at all. It is speeding up. Something is forcefully pushing space itself apart, and we call this mysterious something dark energy. The nature of dark energy is one of the greatest enigmas in modern physics. It appears to be a property of empty space itself, a constant energy density that causes a repulsive gravity, an anti-gravity that drives galaxies away from each other at an ever-increasing rate. What is truly staggering is not just its existence, but its incredibly weak yet perfectly balanced strength. The value of this dark energy is unfathomably small. In the units physicists use, it is about 120 orders of magnitude weaker than what our best theories predict it should be. This is not just a small error. It is the largest and most embarrassing discrepancy in the entire history of science. Yet, this seemingly insignificant weakness is precisely what makes our universe possible. If dark energy were substantially stronger, even by a minuscule amount, its repulsive push would have overcome gravity's pull when the universe was still very young. Galaxies would never have coalesced from the primordial gas. Stars would never have ignited. The cosmos would have been blown apart into a thin, ever-diluting haze of isolated particles with no structure and no chance for life. If, on the other hand, dark energy was substantially weaker or even zero, gravity would have dominated completely. The universe might have expanded for a while, but then collapsed back in a big crunch long before any life could arise. The expansion would have been too brief for the slow, patient work of cosmic evolution. Our universe exists in a breathtakingly narrow window where dark energy is just potent enough to ensure the cosmos expands forever, but weak enough that it waited until galaxies, stars, and planets had already formed before it began its dominant push. We live in the one brief cosmic epoch where we can look up and see a sky full of galaxies. A golden age nestled between a time when the universe was too dense for such structures and a future when they will have been pushed out of sight. Why is the strength of dark energy so perfectly, so improbably tuned for our existence? It is as if a cosmic architect set a dial with impossible precision, creating a universe that is both stable enough to build galaxies and expansive enough to give them room to breathe. Dark energy is not the only ghost in the cosmic machine. While it pushes the universe apart on the largest scales, another invisible force works in opposition, pulling the cosmos together on smaller scales. This is the enigma of dark matter. We cannot see it, touch it, or detect it with any telescope, yet we know it is there because of its immense gravitational grip. It is the hidden skeleton of the universe, the cosmic scaffolding upon which every galaxy is built. Without dark matter, the night sky would be utterly black and empty. After the Big Bang, the infant universe was a nearly smooth soup of hydrogen and helium gas. For galaxies to form, there needed to be seeds, slight clumps of gravity where gas could pool and condense. Ordinary matter alone could not do this job. Protons and electrons, the stuff that makes up everything we see, were under constant pressure from the intense radiation of the early universe. This radiation was so powerful that it prevented ordinary matter from clumping together, like a strong wind blowing away piles of dust. Dark matter, however, is completely different. It does not interact with light or radiation at all. It is immune to that cosmic wind. So while ordinary matter was being buffeted and scattered, dark matter could quietly begin to gather, forming vast, invisible clouds under its own gravity. These clouds of dark matter became the gravitational anchors for the entire visible universe. They created deep wells of gravity that the ordinary gas could not resist. Slowly, over millions of years, the hydrogen and helium gas was drawn into these dark matter halos. Once safely inside these gravitational nests, the gas could cool, condense, and finally ignite into the first stars, lighting up the cosmos. Every galaxy we see today, including our own Milky Way, is embedded within a much larger, massive halo of this mysterious substance. Dark matter is the cosmic architect that designed the blueprint for all structure. The properties of dark matter had to be precisely right for this to work. If it interacted with itself or with ordinary matter too strongly, it would have behaved like a fluid, sloshing around and preventing stable structures from forming. If its particles moved too quickly, a phenomenon known as being hot, they would have escaped their own gravitational pull, smoothing out the universe before galaxies could ever take shape. Instead, the evidence tells us that dark matter is cold and sluggish, allowing it to clump perfectly into the intricate cosmic web we observe. Its presence and its specific, quiet nature were essential ingredients in the recipe for a living universe. This invisible framework, perfectly tuned and perfectly placed, raises a profound question. Why is the cosmos constructed from both the seen and the unseen, in a partnership so delicate that altering one would cause the entire edifice of creation to collapse? This invisible cosmic web of dark matter provides the grand architecture for galaxies, but the tangible world you see and touch is built from something even more fundamental. It is held together by a force of immense power, operating on a scale so small it defies visualization. This is the strong nuclear force, the ultimate glue of reality. Without it, the universe would be nothing but a formless, eternal fog of isolated particles. There would be no atoms, no chemistry, and no us. The strong force is what binds the smallest known building blocks of matter, particles called quarks. Quarks are never found alone. They are perpetually confined, shackled together by this unimaginably powerful force. It takes 3 quarks to make a proton or a neutron, the particles that form the nucleus of every atom. The strength of this binding is almost beyond comprehension. If you could somehow isolate a single quark, the energy required to pull it free from its partners would be so colossal that it would instantly create new quarks from the vacuum, immediately forming new particles. You can never win. The force is so potent that it completely overpowers the electromagnetic force, which tries to push the positively charged protons apart. Within the tiny confines of an atomic nucleus, the strong force creates a binding energy that acts like an unbreakable cement, overcoming the powerful repulsion between protons and locking them together with neutrons into a stable core. But this force had to be perfectly tuned. Its strength exists in a breathtakingly narrow window of possibility. If the strong force were just a few % stronger, the nuclear glue would be too potent. Protons and neutrons would bind together so fiercely that they would rapidly fuse into larger and larger elements, consuming all the hydrogen in the universe. Without hydrogen, the fuel for stars like our Sun would be gone. the cosmos would be dark, filled with giant atomic nuclei but no stars to light them up. Conversely, if the strong force were even slightly weaker, it would fail to overcome the electromagnetic repulsion between protons. Atomic nuclei could never form. The universe would consist only of hydrogen, a solitary proton floating in a sea of electrons. There would be no carbon, no oxygen, no iron, none of the elements essential for planets or life. The delicate nuclear alchemy that forges the elements inside stars would be impossible. This perfect calibration extends even further. The strong force is what allows for the existence of the carbon atom, the fundamental backbone of life as we know it. There is a famous resonance in the carbon nucleus, a precise energy level that allows it to form efficiently inside dying stars. This resonance is a direct consequence of the strong force's specific strength. Tweak the force by even a tiny amount, and that resonance disappears. The production of carbon in stars would plummet, and the universe would be devoid of this essential ingredient for biology. So, from the scale of galaxies down to the heart of an atom, we find the same story of impossible precision. The strong nuclear force is not just a random number in a physics equation. It is a fundamental setting, a dial turned to an exact value that allows for a complex, structured, and living cosmos. Why is this glue of reality so perfectly formulated for building a world that can eventually ask questions about its own existence? While the strong force builds the atomic nucleus, another far more subtle power must govern its transformations. This is the weak nuclear force, a ghostly hand that guides the very alchemy of the stars. Without its precise and delicate touch, the universe would be stillborn, filled with hydrogen but incapable of creating the diversity of elements that make up our world and our bodies. The weak force is the master of change. It is responsible for a process known as nuclear decay, where one type of particle can slowly and spontaneously morph into another. Its most vital role occurs in the heart of every star like our Sun. Deep within that stellar furnace, the intense pressure and heat squeeze hydrogen nuclei together to form helium. This is the first step in the cosmic chain of creation, but this fusion process relies on the weak force to work. When two protons collide at the Sun's core, their positive charges fiercely repel each other. For them to stick and form a new element, one of those protons must transform into a neutron. This metamorphosis is the exclusive domain of the weak force. It is an incredibly slow, patient process. A single proton has only a vanishingly small chance of transforming in this way, which is why our Sun burns its fuel so steadily over billions of years. This slowness is not a flaw, it is a feature of perfect cosmic engineering. If the weak force were significantly stronger, this transformation would happen far too quickly. Protons would turn into neutrons at a rapid rate, causing stars to burn through their hydrogen fuel in a furious, short-lived blaze. A star like our Sun might exhaust itself in mere millions of years, a timescale far too brief for the slow, gradual evolution of life on any orbiting planet. The universe would be filled with the brief, spectacular flashes of stellar lives, but no long-lasting, stable suns to nurture biology. If the weak force were any weaker, the opposite problem would arise. The transformation from proton to neutron would be so sluggish that the chain of nuclear fusion could barely begin. Stars would struggle to ignite or would glow only as faint, cool embers. The universe would remain a dark, primordial soup of hydrogen, with none of the heavier elements like carbon or oxygen ever being forged. The weak force's strength is perfectly poised between these two catastrophic extremes. It allows stars to shine with a stable, enduring light for billions of years, providing the consistent energy life needs to arise and evolve, but its role does not end there. The weak force is also the key that unlocks the universe's greatest treasure vault, the supernova. When a massive star dies, it does not go quietly. It collapses under its own gravity and then rebounds in a cataclysmic explosion that outshines an entire galaxy. In that unimaginable inferno, elements are forged in an instant. The intense flood of neutrons creates atomic nuclei heavier than iron, from the gold in your jewelry to the uranium that powers nuclear reactors. Yet for these newly formed heavy elements to escape the dying star and be scattered across space, the weak force is essential. It allows neutrons to turn back into protons through a different kind of decay, stabilizing the newly minted nuclei and ensuring they can survive their journey across the cosmos. This stellar debris, enriched with carbon, nitrogen, oxygen, and iron, eventually coalesces into new solar systems. Every atom of oxygen you breathe, every particle of carbon in your cells, was once created in the heart of a long-dead star and liberated by the precise workings of this feeble yet vital force. So we find yet another dial on the cosmic control panel set with impossible accuracy. The weak nuclear force, so often overlooked, is a silent partner in creation. Its specific strength determines the lifespan of stars, the very rhythm of cosmic time, and the abundance of the chemical elements that are the bedrock of life. Why is this force of change so perfectly tuned to allow for a universe that is not only structured, but also chemically rich and biologically fertile? The weak force forges the elements, but it is another, more familiar power that gives them their voice. This is the electromagnetic force, the silent architect of chemistry and the master weaver of reality's tangible fabric. While gravity builds the grand stages of galaxies and the nuclear forces forge the atomic actors, electromagnetism writes the entire play. It dictates how every atom will interact with every other, crafting an infinite library of molecules from a finite set of ingredients. Its strength is perfectly calibrated for complexity, significantly stronger, and atoms would cling to one another with such ferocity that chemical reactions would be irreversible locks, freezing matter into inert, unchanging lumps. Significantly weaker, and atoms would be like ships passing in the night, unable to form any stable bonds at all. The universe would remain a monotonous, non-reactive gas. But electromagnetism is just strong enough to allow for delicate, breakable bonds, enabling the dynamic dance of chemistry that is life itself. This force operates on a simple but profound rule, the inverse square law. Its influence weakens precisely with the square of the distance. This is not a minor detail. It is the reason atoms have distinct sizes and molecules have specific, stable shapes. It allows for the intricate machinery of proteins to fold into their functional forms, and for the double helix of DNA to reliably encode information. Think of a simple water molecule. The electromagnetic attraction between the oxygen atom and its two hydrogen atoms creates a specific angle, a V shape that gives water its miraculous properties. This shape makes water a universal solvent, capable of dissolving salts and transporting nutrients through your bloodstream. It gives water a high surface tension, allowing insects to walk on its surface and plants to draw water from their roots to their highest leaves. It is even why ice floats, insulating lakes and rivers so that life can survive winters. Without the precise strength and mathematical rule of the electromagnetic force, water would be just another liquid, devoid of these life-giving quirks. Every sensation you have ever experienced, from the warmth of sunlight to the hardness of a table, is electromagnetic in origin. Your eyes detect electromagnetic waves we call light. Your nerves fire using electrical impulses, which are moving electromagnetic fields. The very thoughts forming in your mind are a storm of electrochemical signals. The entire rich tapestry of the material world, with its colors, textures, and transformations, is a direct consequence of this one force's perfect tuning. It is the brush that paints the world with detail, transforming a universe of simple elements into an arena of breathtaking complexity. Why does this force possess the exact right strength to build not just matter, but intricate, self-organizing, and ultimately living matter? This dizzying precision of the fundamental forces leads us to one of the most profound and embarrassing problems in all of science. It is a puzzle so vast it threatens to unravel our entire understanding of physics. The issue lies with the energy of empty space itself. According to our best theories of quantum mechanics, the vacuum is not truly empty. It is a seething, bubbling foam where virtual particles constantly flicker in and out of existence. This quantum activity should endow every cubic centimeter of space with a colossal amount of energy, a pressure known as the vacuum energy. When we calculate this theoretical value, the number is astronomically large. Yet when we look out at the universe and measure the actual strength of dark energy, the force driving cosmic acceleration, we find a value that is almost zero. The two numbers should be the same, but they are not. The calculated vacuum energy is 10 to the power of 120 times larger than the observed dark energy. This is not a small discrepancy. It is the largest mismatch between theory and observation in the entire history of human knowledge. Writing out that number would require a 1 followed by 120 zeros. To grasp the scale of this error, imagine comparing the energy in a single hydrogen atom to the energy contained within the entire observable universe. The difference between those two is minuscule compared to the gap between our prediction for vacuum energy and the reality we observe. This is the cosmological constant problem, and it represents a fine-tuning of such staggering precision that it defies all rational belief. For the universe to be habitable, for galaxies to form and life to emerge, the actual energy of empty space had to cancel out almost perfectly, leaving behind only the tiniest, most insignificant residue we call dark energy. It is as if a cosmic accountant had to subtract two numbers that were each a googolplex in size, and their final balance was precisely $1. The fact that this near-perfect cancellation happened, and that the tiny leftover is exactly the value needed for our cosmic existence, is a mystery that keeps physicists awake at night. This is not merely a missing piece of the puzzle. It is a screaming signal that our most fundamental ideas about reality are deeply incomplete. Why does the vacuum energy cancel with such impossible accuracy? What hidden principle or deeper law of nature could possibly enforce this breathtaking level of cosmic fine-tuning? This geometric perfection of the vacuum finds its grandest expression in the shape of the cosmos itself. When we map the universe on the largest scales, measuring the subtle wrinkles in the ancient light from the Big Bang, we discover something profound. The fabric of space is geometrically flat. This flatness is not like the flatness of a tabletop, but a precise balance in the geometry of space-time. It means that parallel light rays will never converge or diverge as they travel across the cosmos for billions of years. This observed flatness is not a trivial fact. It is a relic of the universe's first instant, a condition that had to be set with a level of precision that challenges the very meaning of probability. For the universe to be flat today, its density at the moment of the Big Bang had to be exactly the critical density. Imagine a pencil balanced perfectly on its tip. The slightest breath of wind, the tiniest vibration, and it will topple over. The initial density of the universe was like that pencil. For it to have remained balanced for nearly 14 billion years, resulting in the flat universe we see, its initial value had to be fine-tuned to an accuracy of 1 part in 10 to the power of 60. That is a 1 followed by 60 zeros. To grasp this number, consider that the number of atoms in the entire observable universe is only about 10 to the power of 80. The precision required is akin to guessing the exact position of a single, specific atom out of all the atoms in a billion Milky Way galaxies. There is no known law of physics that demands this exact initial condition. A universe born even slightly denser would have collapsed back on itself in a fiery big crunch after only a brief expansion. One born slightly less dense would have flown apart so rapidly that not a single star would have ever condensed from the thinning gas. Our cosmos exists because this one parameter, the initial density, was dialed in with impossible exactitude from the very first moment. Why was the universe born in this state of perfect, precarious balance? This is not a question of later evolution, but of a foundational setting that seems to have been chosen with breathtaking care at the very dawn of time. This geometric perfection extends to a puzzle of cosmic temperature. From every direction we look, the most ancient light in the universe, the cosmic microwave background, arrives at our telescopes with precisely the same temperature. The entire sky is a uniform sea of cold radiation, varying by less than 1 part in 100,000. This presents a profound mystery known as the horizon problem. Regions of the universe on opposite sides of the sky are so distant from each other that light has not had enough time since the Big Bang to travel between them. They have never been in contact, never been able to exchange heat or information to equalize their temperature. How then can they possibly know to be at the exact same temperature? It is as if you walked into a vast, crowded room where thousands of people you have never met from completely isolated communities were all humming the same note in perfect pitch without any prior communication. This cosmic synchrony defies the basic laws of thermodynamics, which state that temperatures only equalize through contact. The universe, in its standard Big Bang model, should be a patchwork of hot and cold spots, a chaotic mess reflecting its disconnected origins. Yet we observe a stunning, almost unnatural uniformity. The solution to this enigma is one of the most elegant ideas in modern cosmology, a concept known as cosmic inflation. This theory proposes that in the very first fraction of a second of its existence, the universe underwent a period of breathtakingly rapid expansion. For a fleeting moment, far briefer than the blink of an eye, space itself expanded faster than the speed of light. This was not matter moving through space, but the fabric of spacetime stretching at an exponential rate. During this inflationary epoch, a subatomic speck of space, smaller than a single proton, was blown up to a size larger than our entire observable universe today. This explosive growth provides the answer to the horizon problem. Before inflation, that tiny primordial seed was small enough for every part of it to be in intimate contact. It was a single, unified, and thermally balanced whole. Then, inflation took this perfectly smooth and uniform patch and stretched it to cosmic proportions, preserving that initial equilibrium across the vast expanse we see today. The entire observable universe is just a magnified fragment of that original, minuscule, and perfectly synchronized domain. Inflation did more than just solve the horizon problem. It also provided the perfect mechanism for creating the seeds of all future structure. The quantum fluctuations that are inherent to empty space, tiny random jitters at the smallest scales, were stretched to astronomical sizes by inflation. These microscopic ripples became the faint, macroscopic wrinkles in the density of the universe. They were the gravitational seeds that dark matter would later cling to, the blueprints for every galaxy, star, and planet that would ever form. In one brilliant stroke, inflation explains both the universe's large-scale smoothness and its small-scale lumpiness. It transformed a cosmic mystery into a coherent narrative of creation, suggesting that the perfection we see was forged in a single, transformative instant at the dawn of time. Inflation's final, brilliant act was to weave the seeds of galaxies from the fabric of nothingness itself. Within that primordial, rapidly expanding space, the vacuum was not truly empty. It was a quantum sea, fizzing with temporary particles and energy fluctuations that popped in and out of existence. These were not real particles in the classical sense, but ghostly, unpredictable jitters in the fields that fill the universe. On their native subatomic scale, these quantum fluctuations were utterly insignificant, appearing and vanishing in moments too brief to measure. But inflation acted like a cosmic amplifier of unimaginable power. As space stretched faster than light, it did not smooth these fluctuations out. Instead, it grabbed these microscopic ripples and stretched them across the cosmos, freezing them into the very fabric of space-time. What was once a quantum whisper smaller than a single proton became a macroscopic ripple light years across. These frozen ripples were tiny variations in the density of the universe. In some regions, space was ever so slightly denser, and in others, ever so slightly more rarefied. This created a faint, invisible blueprint imprinted on the entire cosmos. After inflation ended, gravity went to work on this blueprint. The slightly denser regions, with their extra bit of gravitational pull, began to act as traps. Dark matter, immune to the pressure of radiation, was the first to fall into these gravitational wells. Then, ordinary matter followed, gas and dust slowly pooling into these invisible scaffolds. Over hundreds of millions of years, these overdensities grew, feeding on the surrounding material, eventually collapsing into the first stars and the glittering islands of galaxies we see today. The entire cosmic web, with its vast filaments and glittering clusters, is simply the grown-up version of those infant quantum ripples. Yet the amplitude of these fluctuations, their initial strength, was calibrated with another layer of impossible precision. If these primordial ripples had been significantly stronger, the gravitational seeds would have been too potent. Matter would have collapsed into enormous, voracious black holes almost instantly, or formed monstrous, dense galaxies that would violently tear each other apart. The universe would be a chaotic, destructive place with no stable solar systems capable of hosting life. If the fluctuations had been significantly weaker, the gravitational seeds would have been too feeble. The gentle tug would have been insufficient to gather gas against the pressure of the expanding universe. No galaxies would have ever condensed. The cosmos would have remained a perfectly smooth, ever-diluting cloud of hydrogen and helium, a featureless void with no stars, no planets, and no chance for complexity. The amplitude was just right, strong enough to create a rich tapestry of structure, but gentle enough to allow for the slow, orderly evolution of galaxies and the safe, quiet orbits of planets within them. We are therefore the descendants of a quantum accident, a random shiver in the first moment of time that was magnified into a universe of beauty and structure. Why was the volume of this quantum noise set to the perfect level, allowing for a cosmos filled with galaxies, yet safe enough for life to emerge within one? Yet another perfect number was imprinted upon the universe in its fiery first second. This is the ratio of photons to baryons, a value so fundamental it determined whether the cosmos would be a brilliant but empty light show or a world of solid, tangible things. Baryons are the heavy particles, the protons and neutrons that constitute all the atomic matter we see around us. Photons are the particles of light and energy. In the early universe, these two were locked in a ferocious, constant battle. For every single baryon, there were roughly 1 billion photons. This number, 1 billion to 1, is not a random figure. It is a cosmic constant of breathtaking precision, and it had to be exactly what it is. In that primordial inferno, matter was constantly being created and destroyed. A particle of matter and a particle of antimatter would collide, annihilating each other in a flash of pure energy, becoming photons. Conversely, photons of sufficient energy could spontaneously transform into a particle and its antimatter counterpart. The entire universe was a seething, dynamic equilibrium between something and nothing, but a tiny, almost imperceptible asymmetry existed. For every 1 billion and 1 matter particles created, only 1 billion antimatter particles were formed. That 1 in a billion excess is everything. It is the entire physical universe. All the galaxies, stars, planets, and people are made from that one leftover particle in a billion. The rest annihilated with their antimatter twins in a blaze of light, producing the cosmic background of photons we observe today. This is why the ratio is 1 billion photons for every single proton. Now consider the consequence if this number had been different. If the asymmetry had been smaller, if the excess of matter over antimatter were only 1 in a trillion, then the annihilation would have been far more complete. The leftover matter would have been too sparse, too thinly spread across the expanding cosmos. Gravity, which relies on density, would have been too weak to ever gather this diffuse gas into galaxies and stars. The universe would be a dark, eternal void, filled with the fading afterglow of that great annihilation, but devoid of any structure. On the other hand, if the asymmetry had been larger, if matter had dominated by 1 in a million, the outcome would have been equally catastrophic. With so much more matter surviving the annihilation, the density of the universe would have been far greater. Gravity would have pulled everything together with immense force, causing the cosmos to collapse back on itself in a big crunch long before stars could form stable planetary systems. The universe would have been massive but fleeting. The 1 in a billion ratio was the perfect compromise. It left behind just enough raw material for gravity to work with over billions of years, building a rich cosmic web of galaxies, but not so much that it triggered an immediate gravitational collapse. This delicate balance allowed for a universe that is both full of structure and enduring enough for life to evolve. Why was this cosmic ledger balanced with such exquisite finesse? Our entire material reality hinges on a single, fortunate digit in a number of astronomical size, a ghostly remainder from the universe's very first calculation. The stability of matter itself rests upon the mass of a single, elusive particle. This is the story of the Higgs boson, a cosmic keystone discovered only after a decades-long search. Its mass, measured at 125 billion electron volts, is far more than just a number in a data table. It occupies a razor-thin window of stability, a precarious ledge between 2 cosmic catastrophes. If the Higgs mass were just a few percent larger, the consequences would be immediate and devastating. The Higgs field, which permeates all of space and gives other particles their mass, would become radically different. It would interact with itself in a way that makes the entire vacuum of space unstable. Our universe would not be resting in its true, lowest energy state, but would be perched in a false vacuum like a ball balanced on the tip of a mountain. A random quantum fluctuation could trigger a catastrophic decay, a bubble of true vacuum that would expand at the speed of light, rewriting the laws of physics as it moved. Within that bubble, the fundamental forces and particle masses would be altered, almost certainly rendering atomic nuclei impossible. This cosmic phase transition would be the end of everything we know, and it could happen at any moment. The fact that it has not happened in nearly 14 billion years tells us the Higgs mass is safely below this critical threshold. But what if it were slightly smaller? If the Higgs were even a little bit lighter, it would have a different but equally fatal effect on the structure of matter. The force that binds atomic nuclei, the strong nuclear force, would be thrown out of balance. Protons and neutrons would become significantly heavier, altering the delicate nuclear glue that holds them together. This would make atomic nuclei unstable. Elements like carbon and oxygen would spontaneously fall apart. The universe would be incapable of forming the complex atoms essential for planets, water, and life. Matter would be stuck in its simplest form, a universe of hydrogen and little else. The measured mass of the Higgs boson sits perfectly between these 2 abysses. It is just heavy enough to keep the vacuum of space stable and our reality secure, yet just light enough to allow for the existence of a rich periodic table of elements. This is not a comfortable margin of error. The window of stability is astonishingly narrow. Out of all the possible values the Higgs mass could have taken, the one that allows for our existence is a tiny, specific sliver. We live in a universe where this fundamental parameter was set with the precision of a master watchmaker. Why does this particle, which confers mass upon all others, itself possess the one mass that permits a durable and complex cosmos to emerge? This dizzying cascade of perfect numbers and fortunate accidents forces us to confront a radical possibility. What if the universe appears perfectly designed for life because in a very real sense it has to? This is the core of the anthropic principle, a reasoning that turns the mystery of fine-tuning on its head. It suggests the cosmos is not fine-tuned for us by chance or design, but that we can only exist within a universe that is fine-tuned. Our very presence as observers acts as a filter, selecting for this specific cosmic reality from a vast sea of possibilities. The principle comes in two distinct forms, one cautious and one profoundly speculative. The weak anthropic principle is the simpler, almost tautological version. It states that the observed values of all physical and cosmological quantities are not random, but are restricted by the requirement that there be sites where carbon-based life can evolve. It also requires that the universe be old enough for it to have already done so. We do not observe the universe from a random point in space and time, but from one that is compatible with our existence. We could not find ourselves in the first 3 minutes of the cosmos because there were no atoms, let alone planets or people. We could not find ourselves in a region of empty space between galaxies because there would be no world to stand on. Our location is necessarily privileged, not in a cosmic sense, but in a biological one. We are where life can be. This weak version simply acknowledges the observational bias our own existence imposes. It explains why we live in a universe that is billions of years old, in a quiet suburb of a galaxy orbiting a stable star. It does not, however, fully explain why the fundamental constants themselves allow for such a place to exist at all. For that, some scientists propose the strong anthropic principle. This is the far more controversial idea. It posits that the universe must have those properties which allow life to develop within it at some stage in its history. The word "must" is doing a tremendous amount of work here. It implies a form of cosmic necessity, as if the laws of physics were somehow compelled to permit observers. This version ventures beyond simple observation bias and into the realm of deep metaphysics. Why would the universe be compelled to produce life? The strong anthropic principle does not provide a clear mechanism, but it opens the door to staggering implications. It hints that the existence of conscious observers might be a fundamental feature of reality, as integral to the cosmos as space and time. The constants are what they are because if they were any different, we would not be here to notice. This reasoning is often criticized as being a cop-out, a mere tautology that explains nothing. Yet its proponents argue it is the only logical conclusion from the data. When you are dealt a perfect hand in a card game, you can ask what the odds were. But if you were only allowed to be in the game if you held a perfect hand, then the odds become irrelevant. Your presence at the table is proof you hold the winning cards. Our existence in this universe is the ultimate selection effect. We are the living proof that a universe with these specific laws is possible. The controversy lies in what we infer from this. Does our observation simply reveal a single, incredibly lucky universe, or does it point toward a multiverse, a vast and perhaps infinite ensemble of universes, each with different physical laws and constants? In such a cosmic landscape, most universes would be stillborn or barren, but by sheer probability, a few would, by pure chance, have the right combination for life. We, of course, find ourselves in one of those rare, hospitable ones. The anthropic principle, in this view, becomes the explanation for our local reality without requiring a designer. It swaps the miracle of a single-tuned universe for the staggering improbability of our address within an infinite reality. Whether you find this answer satisfying or deeply unsettling, it forces a humbling perspective. The universe is not necessarily fine-tuned for us. We are simply the ones who are fine-tuned to it, the temporary inhabitants of a narrow band of reality where the numbers just barely add up. This idea of a cosmic lottery finds its most ambitious scientific expression in the multiverse hypothesis. It is a concept that radically reinterprets our place in reality. suggesting that our entire cosmos, with all its galaxies, stars, and laws of physics, is merely one bubble in a frothing, infinite ocean of universes. In this vast cosmic landscape, sometimes called the meta-universe, each separate universe can have its own unique set of physical constants and fundamental forces. In one universe, the strong nuclear force might be too weak to bind protons together, leaving a cosmos of pure hydrogen. In another, gravity could be so strong that every star instantly collapses into a black hole. Most of these universes would be stillborn, barren, or wildly chaotic, utterly incapable of supporting any form of complexity, let alone life. Our universe, then, is not a miracle of design. It is simply the one ticket drawn from an immeasurably large hat that happened to have all the numbers lined up perfectly. We do not live in a universe that was fine-tuned for life. We live in the only type of universe where beings like us could possibly arise to ponder the question. The staggering improbability of our existence is not a puzzle to be solved, but a necessary condition of our observation. We could never find ourselves in a universe where the constants are wrong, because such a place would have no one to do the finding. Think of it like this. If you are dealt a royal flush in a game of poker, the odds are astronomically low. But if you are playing in a tournament with an infinite number of decks and an infinite number of players, someone somewhere is bound to be holding that perfect hand. From the perspective of that lucky player, it feels like a miracle. From the perspective of the entire game, it was a statistical inevitability. The multiverse transforms the question from why are the constants so perfect to, of course, we find ourselves in the rare universe where they are. This idea emerges naturally from some of our most advanced theories in physics, particularly from certain models of cosmic inflation. The same process that smoothed and stretched our early universe could, in theory, be eternal, continuously spawning new pocket universes in an unending chain. Each one inflates into its own reality, with its own random set of physical laws, forever disconnected from our own. The philosophical implications are profound. It suggests that every possible reality, no matter how strange or alien, might exist somewhere in the limitless expanse of the meta-universe. The challenge, of course, is that these other universes are, by their very nature, beyond our observational reach. We are trapped within our own cosmic bubble, unable to see outside its boundaries. For some, this makes the multiverse an untestable, almost metaphysical idea. For others, it is the most elegant and logical explanation for the one undeniable fact of our existence. The multiverse does not make our universe any less special to us, but it does redefine what that specialness means. We are not the center of a single, purpose-built creation. We are the lucky inhabitants of a rare and beautiful oasis in a desert of cosmic silence, a desert so vast that its endlessness guarantees the existence of a few fleeting islands of life. But the multiverse is not the only answer to this cosmic riddle. Another explanation stands in stark contrast, one that takes the fine-tuning at face value. What if the universe is not a random lottery winner, but the product of a cosmic mind? This is the argument for intelligent design viewed through a purely cosmological lens. It proposes that the staggering precision of the physical constants, the perfect balance of forces, and the exquisitely calibrated initial conditions are exactly what they appear to be, evidence of deliberate engineering. The sheer statistical improbability of so many independent factors aligning by pure chance is, for proponents of this view, insurmountable. It is more logical, they argue, to infer that a universe capable of generating conscious life is the result of purposeful design. This is not necessarily an argument for a religious deity, but for a transcendent intelligence, a cosmic architect who set the dials with intention. The universe, in this perspective, is not an accident. It is a masterpiece, a complex system built with a specific function in mind. Much like a watch implies a watchmaker, the philosophical implications are profound. It suggests that mind, not mere matter, is a fundamental feature of existence. consciousness would not be a late-arriving fluke in an indifferent cosmos, but the very reason the cosmos exists in its current form. The laws of physics become a kind of blueprint, a set of instructions written in the language of mathematics to allow for a universe that could eventually understand itself. This idea forces us to confront a deep question about the nature of explanation. Science explains the how of the universe with breathtaking detail, describing the mechanisms that govern everything from quarks to quasars. But the question of why the laws are so life-permitting lies outside the realm of testable science. It resides in the domain of philosophy and metaphysics. Is the universe ultimately a brute fact, a meaningless given, or is it, as the design argument suggests, a product of reason? The fine-tuning in this view is the signature of that reason, etched into the fabric of reality itself. It is a clue that points beyond the physical, to a cause that is not itself subject to the very laws it brought into being. The quest for a single, elegant theory of everything leads directly to this cosmic landscape of possibilities. For decades, physicists have sought a framework that unites the large-scale force of gravity with the quantum world of tiny particles. Their most promising candidate is string theory, a profoundly beautiful and complex idea. It proposes that the fundamental constituents of reality are not point-like particles, but unimaginably small, vibrating loops of energy or strings. The different vibrations of these strings, much like the distinct notes on a guitar string, give rise to the entire menagerie of particles we observe, from electrons to quarks to photons. This single concept promises to weave gravity and quantum mechanics into a seamless whole. Yet this elegant unity comes with a staggering consequence, one that directly addresses the mystery of our perfect universe. The mathematics of string theory does not yield one unique set of laws. Instead, it predicts an astronomical number of possible solutions, a veritable landscape of potential realities. Current estimates suggest there could be 10 to the power of 500 distinct vacuum states. That number is so vast it exceeds the number of atoms in our observable universe. Each of these vacuum states corresponds to a different way for the extra dimensions, which string theory requires to be curled up and compactified. And each unique configuration results in a different set of effective physical laws and constants in our four-dimensional world. The strength of the electromagnetic force, the mass of the electron, the value of the cosmological constant, all of these would be different in each pocket of this landscape. String theory thus provides a potential physical mechanism for the multiverse. Our universe is not a singular, lonely entity. It is one bubble in a frothing cosmic foam, one valley in an endless mountain range of possibilities. In this vast landscape, most universes are dead, with constants that prevent any structure from forming. But in an inconceivably large number of possibilities, a few will, by pure chance, have the right combination for stars, planets, and life. Our existence here is not a miracle of design, but a statistical certainty in an infinitely varied reality. We are not the purpose of the cosmos, but we are a beautiful and natural expression of its limitless potential. Carbon is the silent architect of life, the universal element of complexity. Its unique talent lies in its atomic structure, with 4 available bonds that allow it to link with other atoms in an endless variety of ways. It can form long, stable chains, intricate rings, and sprawling 3-dimensional networks. This versatility is what builds the vast library of organic molecules, from the simple methane in natural gas to the dizzying complexity of DNA. No other element in the periodic table comes close to this creative potential. Silicon is sometimes suggested as an alternative, but its bonds are weaker and less stable, incapable of forming the intricate, delicate structures that biology requires. The universe, it seems, has placed its bet on carbon. But for that bet to pay off, carbon had to exist in abundance, and its creation inside stars required a series of cosmic coincidences so precise they seem almost miraculous. The journey of a carbon atom begins in the heart of a dying star. When a star much larger than our Sun exhausts its hydrogen fuel, its core begins to fuse helium. Two helium nuclei, each with 2 protons and 2 neutrons, can collide to form a temporary, unstable nucleus of beryllium. Under normal circumstances, this beryllium would fall apart in a fraction of a second. But inside the intense, searing heat of a stellar core, a third helium nucleus can strike this fleeting beryllium nucleus before it has a chance to disintegrate. This three-way collision forges a nucleus of carbon. For this to happen efficiently, the energy levels of the carbon nucleus had to be perfectly aligned. There needed to be a specific resonant energy state that acted like a welcoming harbor, dramatically increasing the odds of this triple collision sticking. In the 1950s, the astronomer Fred Hoyle famously predicted that such a resonance must exist, purely from the logical necessity that we are here made of carbon. When nuclear physicists tested this, they found Hoyle was exactly right. The carbon nucleus possesses a resonant state at precisely the right energy to allow for its prolific production in stars. Without this precise nuclear resonance, the triple helium process would be hopelessly inefficient. Stars would produce only trace amounts of carbon, sputtering out this essential element instead of manufacturing it in stellar factories. The universe would be a carbon-poor desert, devoid of the molecular diversity needed for life, but the fine-tuning does not stop there. The very same process that creates carbon could also destroy it. Once carbon exists, it can easily fuse with another helium nucleus to form oxygen. For life to be possible, this reaction must also be carefully balanced. If the oxygen nucleus had a similar resonant energy level, it would act as a voracious sink, gobbling up nearly all the carbon as soon as it formed. Stars would convert their carbon into oxygen with ruthless efficiency. Yet the oxygen nucleus has a resonance that is just slightly off, just a fraction higher in energy. This tiny discrepancy makes the carbon-to-oxygen reaction less likely, allowing significant amounts of carbon to survive the stellar inferno and be scattered into space when the star explodes. The result of this dual fine-tuning is a universe with a nearly perfect balance of carbon and oxygen, two elements that are the fundamental building blocks of life as we know it. We are carbon-based life forms in a universe that seems to have gone to extraordinary lengths to ensure carbon's abundance. This is not a minor detail of nuclear physics. It is a central pillar in the architecture of a living cosmos. Why do the atomic nuclei possess these specific, life-giving resonances? Was it mere luck in the quantum rules, or does the universe inherently favor the chemistry of life? This longevity of the carbon atom is built upon an even deeper, more profound stability. The very protons at the heart of every atom are themselves monuments to cosmic endurance. We are made of stuff that has lasted for nearly 14 billion years, and this is not a trivial fact. It is another perfectly set dial on the control panel of reality. A proton, according to our best theories, should not be perfectly stable. Grand unified theories, which attempt to merge the electromagnetic, weak and strong forces, suggest that protons can decay, transforming into lighter particles over immense timescales. We have hunted for this decay in vast, underground detectors filled with ultra-pure water, watching for the telltale flash of light that would signal the death of a single proton. So far, we have seen nothing. The experiments tell us that the proton's lifetime is staggeringly long, at least 10 to the power of 34 years and likely far longer. To grasp this number, consider that the current age of the entire universe is only 10 to the power of 10 years. A proton lives for a duration that is a trillion times longer than the cosmos has even existed. This incredible longevity is absolutely essential for our existence. If protons decayed significantly faster, say in just a few billion years, the very fabric of matter would unravel. Complex structures could not hold together over the vast stretches of time required for biological evolution. Planets would literally disintegrate, their atomic nuclei dissolving away. Stars would fade as their fuel vanished. Life, which depends on stable, persistent matter, would be impossible in a universe where the building blocks themselves have a short expiration date. Yet the opposite scenario is equally revealing. If protons were truly perfectly stable, if they could never decay under any circumstances, it would paint a very different picture of the universe's ultimate fate. In a cosmos where all matter is eternal, the far, far future would be dominated by a slow, cold decay powered by quantum tunneling, where every structure eventually evaporates into radiation over incomprehensible eons. The fact that protons might decay, even on these almost unimaginable timescales, suggests a deeper connection between the forces of nature and hints that our current universe is a temporary, albeit incredibly long-lived phase. The observed stability of the proton is therefore another Goldilocks condition. It is not so unstable that complex matter falls apart before life can arise, yet not so perfectly stable that it precludes a deeper unity in the laws of physics. It exists in a sweet spot that allows for both the persistence of complex structures and the potential for a grand cosmic narrative. We are built from particles that are stable enough to provide a lasting home, yet whose potential fragility whispers of a deeper, more unified reality. This pristine order at the beginning of time is the ultimate enigma. We call this concept entropy, a measure of disorder or randomness in a system. The natural tendency of the universe is for entropy to increase, for things to move from order to chaos. A hot cup of coffee cools down, its heat dispersing into the room. A sandcastle on the beach is slowly eroded by wind and waves. These are examples of the universe progressing toward a state of higher entropy, a featureless equilibrium. Yet the cosmic starting point defies this fundamental rule. The Big Bang did not begin in a state of maximum chaos. It began in a state of incredibly low entropy, a condition of exquisite and unnatural order. This is the ultimate free lunch, a gift of order that the universe has been spending ever since. All the complexity we see, from swirling galaxies to beating hearts, is powered by this initial windfall of order. The stars can shine only because there is a vast, cold space to dump their waste heat. Life can evolve only because the sun is a hot, ordered source of energy radiating into a cold, dark sky. Every process that builds something complex does so by increasing the total disorder elsewhere. We are eddies in a cosmic river flowing inexorably toward a state of uniform blandness. So why was the river's source so improbably pure? The initial low entropy is more baffling than the fine-tuning of any single force. It is easier to explain why a clock keeps good time than to explain why it was fully wound in the first place. To grasp the sheer statistical improbability, picture a brand new deck of cards perfectly sorted by suit and value. This is the low entropy beginning. Now shuffle that deck just once. The order is mostly gone. The universe we see today, with all its structure, is like that single shuffle. It has only moved a tiny way from its initial order toward total disorder. The real mystery is why the deck was ever in that perfectly sorted state to begin with. A random, chaotic origin should have produced a high-entropy mess from the start, a cosmic deck that was already thoroughly shuffled. There would have been no temperature differences, no energy gradients, and therefore no driving force for anything to happen. Time itself would have no clear direction. The universe would have been stillborn, a formless, lukewarm soup forever. The fact that it was not, that it began in a state of pristine order, is the foundation upon which all of history is built. This initial condition is the one setting that seems truly unnatural, a cosmic anomaly that begs for an explanation beyond pure chance. Where did this profound order come from, and why did our universe get such a miraculous head start? This deep order we find etched into the universe's origins and laws is mirrored by a second, equally profound mystery, one that lives in the notebooks of every physicist and engineer. Mathematics, a seemingly abstract invention of the human mind, describes the behavior of the physical world with an accuracy that is both breathtaking and deeply unnerving. The physicist Eugene Wigner called this the unreasonable effectiveness of mathematics in the natural sciences. Why should a system of logic and symbols we devised ourselves fit the reality of a distant quasar or the spin of an electron with such perfect precision? It is as if we discovered a key that fits a lock we never built. Consider the humble quadratic equation. It can predict the arc of a baseball, the orbit of a planet, and the focusing of light in a telescope with flawless results. The number pi, the ratio of a circle's circumference to its diameter, appears unexpectedly in the physics of pendulums, the distribution of river lengths, and the structure of DNA. Even more abstract mathematical concepts, developed centuries ago with no thought of practical application, later turned out to be the essential language for describing reality. Complex numbers, once dismissed as imaginary playthings, are now the foundation of quantum mechanics, without which our computers and lasers would not exist. This is not a matter of us forcing nature to fit our equations. We repeatedly find that the mathematics we invent in the quiet of our studies is already waiting for us in the noisy, complex data of the cosmos. It feels less like we are inventing mathematical laws and more like we are discovering them, uncovering a pre-existing cosmic code. This suggests an underlying rationality to the universe, a deep, logical structure that operates according to consistent mathematical rules. The cosmos is not a chaotic jumble, it is a realm of order that our minds, through mathematics, are somehow able to access and comprehend. This leads to a staggering implication. The universe is not just described by mathematics, it is mathematical in a very fundamental way. From the quantum world to the cosmic scale, the substance of reality appears to be information, relationships, and structure, all governed by mathematical principles. The fact that our minds can tune into this frequency, that we can decode this cosmic software, feels less like a lucky accident and more like a feature of a universe built on reason. Are we simply uncovering the inherent grammar of a cosmos that was, in a sense, always meant to be understood? Yet this grand cosmic architecture is not without its violent imperfections. Our universe is also a shooting gallery filled with existential threats that could erase life in an instant. A large asteroid impact, like the one that ended the age of the dinosaurs, is a constant statistical possibility. From the depths of space, gamma-ray bursts unleash the most powerful explosion since the Big Bang, and if one were to strike our planet, it could sterilize the surface with a wave of intense radiation, stripping away the ozone layer and triggering an ice age. These are not theoretical risks, they are part of the chaotic environment in which our planet exists, a reminder that the cosmos is both a cradle and a battlefield. Even our own sun will not remain stable forever. In several billion years, it will swell into a red giant, engulfing the inner planets and rendering Earth uninhabitable long before. And on the grandest scale, the universe itself is marching toward a bleak and inevitable end. The accelerating expansion driven by dark energy points toward a final state known as the heat death, a time when the last star flickers out and all matter is scattered so far apart that the cosmos becomes a cold, dark, and lifeless void. Given these overwhelming dangers and this ultimate futility, can we truly call the universe perfect? The fine-tuning of the constants allowed life to emerge, but the environment it created is brutally hostile to its long-term survival. Perhaps perfection is the wrong word. A more accurate description might be that the universe is merely suitable, or just barely permissible, for a certain fragile kind of life to exist for a very limited window of time. We are not living in a perfectly safe paradise. We are clinging to a tiny, temporary oasis in a vast and dangerous desert. The real miracle is not that the cosmos is perfectly safe, but that it is just barely safe enough for just long enough for us to have appeared at all. The sheer number of these cosmic coincidences is overwhelming. From the impossibly precise force of gravity to the ghostly strength of dark energy, from the specific resonances in atomic nuclei to the pristine order of the Big Bang itself, every single layer of reality appears fine-tuned. The universe is not governed by a single lucky number, but by an entire symphony of them, each playing in perfect harmony to create a cosmos that can build stars, forge planets, and eventually give rise to conscious life. We are the products of a cascade of perfect conditions, a chain of cosmic necessities so fragile that altering any single link would have rendered the universe stillborn or left it a formless, eternal void. This breathtaking collection of coincidences forces upon us the most profound questions we can possibly ask. Are we the winners of the ultimate cosmic lottery, a one-in-a-Googleplex fluke in a single, lonely universe? Or does the staggering improbability point toward a deeper reality, perhaps a multiverse of infinite possibilities where every potential set of laws plays out? Could it be that the universe is not an accident but a product of mind, a grand design whose purpose is woven into the very fabric of space and time? The answers we lean toward shape our entire understanding of existence, from our sense of purpose to our place in the grand scheme of things. We are left standing in awe before a universe that seems to whisper of a reason behind its laws. What do you believe? Does this mountain of evidence suggest a perfect universe, a designed universe, or simply an incredibly fortunate one? Share your thoughts in the comments below.